After completing this chapter, you should be able to understand the principles of operation of a four-stroke diesel engine. The working cycle of a four-stroke engine takes place within 2 whole revolutions of the crankshaft and consists of the following 4 strokes: an intake stroke, a compression stroke, a power stroke, and finally an exhaust stroke. Marine diesel engines convert the chemical energy contained in a fuel, firstly into the thermal energy of the hot gases, and then into mechanical energy and work on the crankshaft. The energy balance shows that, for a modern marine 4-stroke diesel engine, about 49% of the fuel energy can be converted into mechanical energy available at the propeller shaft. Theoretically, about 15 kilograms of air is needed in order to burn 1 kilogram of a typical liquid fuel. Practically, due to the short time available for combustion, it is necessary to deliver about 30 to 45 kilograms of air for each kilogram of fuel to make sure that we get complete combustion of the fuel. The additional air also helps to cool the cylinder. The combustion air is cooled down before it enters the cylinder. Cooler air is more dense, so we can get more mass into a given volume. The air needed for combustion is usually delivered by a turbocharger, which increases the air pressure to around 3 bar. Because it has been compressed, the air temperature rises to about 200 degrees Celsius, and we therefore need to cool it back down to about 40 to 60 degrees Celsius. The main aim of cooling the air down is to increase its density and deliver enough air to completely burn all of the fuel injected. The intake stroke starts when the piston is in the topmost position, called top dead center, and ends when the piston is in the lowermost position, called bottom dead center. The inlet valves are fully open. The scavenge air enters the cylinder through the inlet valves, which are opened shortly before TDC. The scavenge air pushes out the remaining exhaust gases through the exhaust valves, which are still open at this point. In order to prevent the loss of too much scavenge air, the exhaust valve should be closed shortly after the piston starts to move down. The compression stroke starts when the piston is in the lowermost position, called bottom dead center, and ends in the topmost position, called top dead center. In order to prevent the loss of too much scavenge air, the inlet valve should be closed shortly after the piston starts to move up. The compression pressure can reach 70 to 100 bar, and the compressed air temperature has to be high enough to make self-ignition of the fuel possible. The compression stroke ends with the piston in the top position, top dead center, TDC. The power stroke starts at top dead center, just after fuel injection has started. The power stroke ends at bottom dead center, and the exhaust valves open just before this. Fuel injection usually starts just before top dead center. The actual fuel combustion starts slightly later than fuel injection, because the sprayed fuel drops have to be heated by the compressed air, vaporize, and then ignite. This period is called a self-ignition delay. The temperature in the combustion chamber increases rapidly when combustion starts and can reach as high as 1900 degrees Celsius. The pressure in the combustion chamber also rises rapidly and reaches about 150 to 200 bar maximum, and then decreases as the volume in the cylinder expands and work is done as the piston moves down. The exhaust stroke starts at one bottom dead center and ends at the next top dead center. The exhaust valves are usually opened shortly before bottom dead center, so the very hot exhaust gases can quickly start to escape from the cylinder, and during the exhaust stroke they will be pushed out by the piston moving upwards. Scavenging is the process of pushing exhaust gases out of the cylinder and replacing them with fresh air. The inlet valves open well before the piston reaches top dead center, and the exhaust valves are still open. But the pressure of the gases remaining in the cylinder is lower than the pressure of the scavenge air. This prevents exhaust gases from flowing back into the charge air receiver, and is necessary for a proper scavenge process, which should force out as much of the exhaust gas from the cylinder as possible. In the four-stroke cycle, the piston pushes out most of the exhaust gases, so there is less scavenging of the exhaust gases by the fresh air charge coming into the engine. The gases leaving the cylinder continue to expand in the exhaust duct, and are still at around 350 to 400 degrees Celsius when they enter the turbocharger. In the turbocharger, we extract more energy from the exhaust gas as it drives the turbocharger. The fuel necessary for combustion is compressed in a fuel pump and then delivered to an injector which sprays it into the combustion chamber. The combustion chamber is the space between the top of the piston and the cylinder head. The fuel pump consists of a cylindrical barrel and a plunger. The plunger can typically be rotated in order to control the amount of fuel injected. The plunger is moved upwards against a powerful spring by a push rod connected to a roller. The roller is moved by a cam, which is fixed at the camshaft, but the camshaft itself is driven via a chain or a gear from the crankshaft. In the four-stroke engine we are looking at here, the camshaft rotates at half the speed of the crankshaft. This is not the case for the two-stroke engine, where the camshaft rotates at the same speed as the crankshaft. When the roller is on the unprofiled part of the cam, the plunger stays at its bottom dead center, and the fuel pressure is approximately 3.5 bar. As the camshaft rotates, the plunger starts to be on the profiled part of the cam. The plunger is then pushed upwards, causing a pressure increase inside the barrel. When the pressure inside the fuel pump reaches the residual pressure inside the line to the injector at about 60 bar, the non-return valve on the top of the fuel pump opens, and the fuel pressure starts to build up in the line to the fuel injector. When this pressure wave reaches the injector opening pressure, typically 250 bar, the injector needle valve opens and the fuel starts to spray inside the cylinder chamber through the injector nozzles. As the fuel pump plunger continues to move upwards, the pressure continues to rise, increasing the injection pressure, which can reach as high as 500 to 1,500 bar. The injection process ends rapidly when the helical groove machined in the plunger connects with the spill port in the fuel pump. This causes a rapid fall in the injection pressure, and once this is lower than the injector opening pressure, the injector needle valve will close. As the cam continues to turn, the plunger moves down. On the downward stroke of the fuel pump, low-pressure fuel delivered by an external feed pump enters the fuel pump barrel. The fuel pump is then ready for the next cycle. The moment when the injection ends depends on the effective stroke of the fuel pump. This depends on the angular position of the plunger groove against the spill port. This position can be changed by turning the plunger inside the barrel by a rack and pinion at the lower part of the plunger. If you watch the animation carefully, you would have seen how the fuel rack moved back and the fuel quantity decreased. Replay the page if you want to see this again. This chapter is to give you a short introduction to the main parts of a four-stroke diesel engine. We will be looking in more detail at some of these parts in later chapters. Four-stroke marine diesel engines are also called medium-speed or high-speed diesel engines because their maximum speed is in the range between 400 and 2000 rpm for medium speed and 2000 to 4000 rpm for high-speed engines. Here you can see the four-stroke engine main components visible from the flywheel end. Here you can see the four-stroke engine main components visible from the air receiver side. Here you can see the four-stroke engine main components visible from the non-flywheel end. Here you can see the four-stroke engine main components visible from the fuel pump side. End of this chapter, you should be able to identify the stationary parts of a four-stroke diesel engine and state their function. The cylinder block forms the housing which holds the cylinder liners and has to withstand all the mechanical forces and torques whilst providing rigid support for the crankshaft. The charge air receiver is usually integrated within the cylinder block. The lubricating oil sump is fitted below the cylinder block and is used for collecting the oil after it has lubricated the bearings, etc. The liner is the stationary cylinder which the piston moves in. The liner and the piston form the combustion chamber where the fuel is burned. The critical region of any cylinder liner is the upper section, where the temperature and pressure conditions are highest and therefore most difficult. This is why cylinder liners need to be cooled, so that they maintain their strength. The cylinder head fits over the cylinder liner and forms the upper part of the combustion chamber. Many other important engine parts, like the inlet and exhaust valves, the fuel injector and the starting air valve, are located in the cylinder head. We will also take a look at some of the moving parts connected with the cylinder head whilst we are in this section. The push rod is operated by a profiled cam on the camshaft and moves a rocker arm, which then opens the inlet or exhaust valves. The rocker arm is an oscillating lever that converts the movement of the push rod into linear movement of the inlet or exhaust valve to open it. When the outside of the arm is allowed to return due to the camshaft rotation, the inside rises, allowing the valve spring to close the valve. When opened, the inlet valve passes the scavenge air from the air receiver into the combustion chamber. It is usually closed by a spring and opened by the camshaft via a push rod and rocker arm. The exhaust valve passes the hot exhaust gases from the combustion chamber to the exhaust pipes. It is also usually closed by a spring and opened by the camshaft via a push rod and rocker arm. The fuel injection valve sprays fuel into the combustion chamber. The fuel is delivered by a fuel pump, which is driven from the camshaft. The cylinder head cover fits over the cylinder head and covers the rocker arms and push rods. This reduces noise and heat emissions to the surroundings and prevents loss of lubricating oil. The turbocharger consists of two main parts, mounted on a common shaft. The exhaust gases are used to drive a turbine mounted on one end of the shaft, and this drives the air blower at the other end of the shaft. The air blower draws air in from the engine room, compresses it, and supplies the scavenge air at a pressure higher than atmospheric. After the turbocharger, the gases are led out to atmosphere via an exhaust duct to the funnel. Typically, a medium-speed engine will have one turbocharger. The air cooler is needed to cool down the air coming from the turbocharger. When the air is compressed, its temperature rises, and we need cool air which has a higher density, enabling us to get a greater mass of air into the cylinder. The cool air also helps to cool the combustion chamber during the scavenge process. In this chapter, you should be able to identify the moving parts of a 4-stroke diesel engine and state their function. Let's start by looking at the piston. The piston seals the cylinder and forms the combustion chamber. It is used to compress the air required for combustion and for transferring mechanical energy during the power stroke. The almost flat upper part of the piston is called the piston crown, and the cylindrical lower part is called the piston skirt. The gudgeon pin is fitted through the piston and forms the bearing surface for the top end of the connecting rod. The connecting rod connects the crank pin of the crankshaft with the gudgeon pin of the piston. The upper part of the connecting rod performs an oscillating motion and reciprocating motion, whilst the lower part performs a circular motion. The crankshaft is turned by all the connecting rods, cranks. It performs the final conversion between the reciprocating motion of the pistons and the circular motion of the shaft. The flywheel is a rotating disc used to store rotational energy. This energy is accumulated during the power strokes of the cylinders and then delivered to the shaft between the power strokes, in order to smooth out fluctuations in the engine rotational speed.